data analyst to a new video from Data Analyst KSA. So in this video, we will continue discussing the important topic of probability distributions. In the previous video, we talked about what is a probability distribution, we talked about the probability density and mass functions, and the cumulative distribution function, and we slightly mentioned why is it important or why is it significant to model our real-life problems or real-life events in a probabilistic manner that is common for understanding. And we said that it can solidify your inference for the different estimates that you make for probabilities or even point estimates, statistical summaries of that event. So in this video, we will talk about these common probability distributions that frequently appear and will frequently help you in solving or modeling real-life situations. So we talked about the idea of a sample, the statistical distributions, the different mass and density functions, and the cumulative distribution functions. Now we will talk about the distributions that appear in real-life events, and we will see how we can utilize them. So the ones we will go through are the uniform distribution, the normal distribution, the exponential distribution, and the gamma distribution. And these are for continuous random variable. And we will also talk about the binomial distribution and the Poisson distribution, which are for discrete random variables. So if you think about it, our random variable is the measure that we are actually trying to model. So let's say, for example, it's height. So height is a continuous variable, so it will fall under the continuous random variable distributions. But if we were, for example, trying to model counts, so we are counting the number of goals or the number of successes or the number of let's say cured patients, then we're talking about 1, 2, 3, 4, so we're talking about discrete. So probability distributions split into continuous distributions and discrete distributions, and as mentioned in the previous video, the continuous have probability density functions and the discrete have probability mass functions. And to understand, if you don't understand this very well, you can go through the previous video to make your understanding very intuitive. So without further ado, let's jump into the uniform distribution. So when do we use the uniform distribution? The uniform distribution is used to model events that have equal probabilities of outcome. So let's say we have equal probabilities between two known values. So let's say that the minimum value can be 0 and the maximum value can be 100, but any value between have the same probability of appearance. So what is a good example for that is a random number generator. So if you want to generate a random number between 0 and 1, for example, you want your device to generate 0.95 or 0.9675, you would use something like a uniform distribution. You don't want to give any more preference to any number. So you want everyone to have the same equal probability. And for this, you would use a random number generator. So how would the probability density function look like? So as mentioned, everything has equal probability, so it should be just a horizontal line because there are no spikes, there are no areas where you have more or less probability. Every single number has the same density of appearing in our sample. So apparently, because we are normalizing the probability density function, so it should integrate to 1, so that value should be 1 over b minus beta minus alpha. So if you actually try it out, this will integrate to 1 between a and b. So it makes it a proper probability density function. So what parameters, as we mentioned in the last episode, one of the useful things about modeling our real-life events with a common probability model is that we will only need a few parameters and we will understand everything about the distribution. So what parameters do we need for a uniform distribution? Very intuitively, it's the minimum and the maximum. So it's alpha and beta, or A and B. So as long as I know what are my limits, I know that everything between those two limits have the same probability or has the same density of appearing in my sample. So I only need A and B. The way I note this distribution for a random variable, I would say X tilde uniform A and B. And just by knowing this, I would exactly know the probability density and the cumulative distribution function of that random variable. So the PDF, as we mentioned, it's constant throughout the period between A and B, and it's 0 otherwise. So we represent it as shown here, 1 over B minus alpha, or beta minus alpha, and it's supported for x values between A and B. The CDF, if you think about it, we said the CDF is the cumulative density, or the cumulative distribution. So I'm basically integrating over every single value between A and B. So because it's a horizontal line, these values will add kind of proportionally. So it will be the same value for every increment. So it will be a straight line between A and B. What about the probabilities before A? So if x is smaller than A, I will have 0 value, because I have no density or no numbers in my population that are below A, so everything will be 0. And anything that is above B, so if you remember the cumulative distribution function definition, it's the probability of x being less than a value. So what is the probability of x being less than b plus 1, for example? It's 100%, because all my population is between the minimum and the maximum. So if I go any point above the maximum, it's always going to be 1. And if I go less than the minimum, it's always going to be 0. And between those numbers, it will increase linearly. So this is how the cumulative distribution function for the uniform distribution looks like. And again, if you remember, we said that to get the CDF from the PDF, you integrate the PDF. So go ahead and try it and make sure that you actually get this number or this formula. So you would have 3 periods for your integral, and each period, one is from 0 to A, and one is from A to B, and one is from B to infinity. And once you get the integral of each period, it will look like the CDF we have over here. So now the value of knowing the common distribution that my data follows is that I would know the expected value. So the expected value, if I take, for example, 1000 numbers between A and B, the average of these, which is the expected value, is going to be A plus B over 2. So basically it's going to be the middle point between those two is my average or my mean of my sample. And actually, if you notice here, the formula for calculating the expected value, it's the integral of x times f of x. F of x here is my probability density function. You can also try it out and you will get A plus B over 2. Now I can also get the variance. So the variance of the random variable is the expected value of the random variable squared minus the expected value of the random variable all squared. So expected value, expectation of x squared minus expectation of x all squared. And you will get b minus a squared over 12. So these values would help you understand your population once you know that your population is uniformly distributed between A and B. Now I want to show you the real life examples where you would use such a distribution. So let's say you're trying to guess a birthday. So the birthday, let's say it's can be any day between January 1st and December 31st. So one from 365 possible days. So guessing any birth date is a uniform distribution. There is no preference for a date for a specific random person that you are getting to be falling under. So the person can be born in any day, so every day has an equal probability, so your density will be uniform. Also a raffle ticket. So for example, the raffle tickets are generated between 0 and let's say 10,000 or 100,000 tickets. Every ticket have a similar or equal chance of getting selected. So this ticket, the ticket population represents a uniform distribution. Choosing a card from a deck of cards. Because the cards in a deck of cards each have a probability of 1 over the number of cards in the deck of cards, so every single one has the same probability of getting selected. And this follows a uniform distribution. Spinning a spinner, assuming that the spinner has an equal distribution of weight or it's balanced. Once you spin it, getting any value in that spinner, let's say in a roulette game or in a Wheel of Fortune game, getting any value is a uniform distribution. It can be of any value. So once you know it follows a uniform distribution, you can answer questions like what is the probability of getting a certain number, what is the probability of getting a number that is between this and that, what is the probability of getting a number that is smaller than this. Now we will move into the normal distribution. So when do we use the normal distribution, or when do we see the normal distribution? The normal distribution can be seen in real life variables or factors that cluster around a certain mean. So let's say we are talking about the height of adult males around the world. We will see that there's a certain mean that most of us fall around, with a variance that goes above and below. So we can say that the average of that distribution is here, and most of our population falls within that average. And as we go far from the average, the values go less and less. So this is something that we have seen many times before. It's the bell curve. So the bell curve is the normal distribution, and it's basically the idea of everything being symmetric. So whatever goes on the right side and the left side are the same around a mean value. So basically I have a mu, which represents the mean, and I have a value. Once I apply, I plug that mu into my probability density function, I will see, because it integrates to 1, that this is the value where mu appears. It's 1 over sigma, which is the standard deviation, times square root of 2 pi. So what parameters do I need to understand a population that is normally distributed? I very simply need 2 parameters only. I need the mu, and I need the standard deviation or the variance, which is sigma squared. So standard deviation is sigma, variance is sigma squared. So once I know those two, I can tell everything I want to tell about inferring probabilities, variance, mean, mode of a population that is normally distributed. The notation is x, my random variable, n for normal, mu, and sigma. Again, once I know this, I know everything I need to know about my population. So this is why probability distributions that are commonly known are useful, because once you know them, you can claim that you know everything about your population. Any question of the probabilities, any question that you want to infer the answer of from your population can be given by the cumulative distribution function or the probability density function, which you can know as soon as you know the common probability distribution your population follows. So the probability density function might look a little bit complicated, but it's basically a value that is dependent on the sigma, the standard deviation, multiplied by e, which is the Euler coefficient, e to the minus 1.5 x minus mu over sigma all squared. So this is your PDF. And I'm not going to show the CDF because it includes the error function of it, but I want to show you, every time I will show you the page of Wikipedia gives a very good summary of what is a distribution. So you can see over here, it talks about the normal distribution. It will show you the parameters, how is it parameterized, mu and sigma squared, or mu and sigma, and the PDF, the probability density, and the CDF, the cumulative distribution function, which will look like this one. And it changes its tilt, or it changes the width and let's say the centrality because of the variance. So if my variance is very high, it will be more flat. If my variance is low, everything will be squeezed around the mu value. Now, what is the expected value of a variable that is normally distributed? It is mu, because mu has the highest probability of appearance, as you see in my bell curve here. So for example, if we're talking about adult male's height, it will be the average of the adult male's height around the world. So this will be my expected value of the population. The variance will be sigma squared, which I know from the parameters of the distribution. And it can be estimated by the variance of the sample I collect, if my sampling is done correctly. Now let's talk about a few important notes specifically about the normal distribution. So there is something called the central limit theorem. We will probably cover it in a separate video, but let me just give you the idea. It's a very impressive theorem. It basically tells you that for any random variable in real life, if you collect enough samples from your population, it will basically follow a normal distribution. You will notice that the data has a specific mean that it's kind of clustering around. So if you take, for example, the weight of trees around the world, you will see, for example, the weight of trees follows a specific distribution that looks normal. And this is the central limit theorem, because everything is kind of around a specific center that, if known, can estimate any distribution that we know in real life. Read about it, and I will cover it in a separate video. Another important note is the standard normal distribution. So many times we're not specifically interested about the mu value, but we're interested to see how people differ from that mu value. So let's say we have a test that we are doing for our cohort. So if let's say we're not specifically interested in the average of the class, but we're interested in how every student ranks in the class. So the standard normal distribution subtract the mu, so everything is centered around 0, and it divides by the standard deviation, so everything has a standard deviation of 1. So basically the data will have a standard deviation of 1, and it's centered around the mu of 0. So it will be easy to tell how far or how many standard deviation every point is away from the mean, which is 0. So it's commonly used to standardize the normal distribution. Now there's an important relationship that I want to highlight here, which is the relationship of the normal distribution to the linear regression. So if you remember, when we do a linear regression, basically if we have specific data that is of a response variable y given a covariate or an explanatory variable that is x, we try to fit the best fitting line, which can be done in the maximum likelihood estimation or can be done with the overall least squares method. But basically we will try to minimize the error and find the line that fits the most. And the equation of this line will be the equation of my linear regression. So I will estimate y by b0 or beta 0 plus beta 1 times x. So it will have a slope and it will have an intersection when x equals 0, which is beta 0. But however, my points will not exactly fall on that line. So I have an actual error. So I add this error to my linear regression function. And this normal error is normally distributed. So one of the main assumptions in a linear regression is that once I model the intersection or the intercept plus the slope, everything else will be normally distributed. So I expect the values to have an average of 0, which is a mu value of 0, and the standard deviation or a variance of sigma squared. What does this mean exactly? So the error is this distance. So for example, this point, if we're using the linear regression to calculate the estimate of y, it will be over here, right? But there's an error that is putting the actual point over here. So this is my error, and my error follows a normal distribution. So for example, if you think about it, if you imagine a normal distribution curve that is fitted, you can see that most values should fall here, but there's a probability that the value will fall here. There's a less probability that it will fall here. There's a less probability that it will fall here. However, there is a probability that every value can appear in my normal distribution. If you think about this point, it's falling where the highest probability is. If you think about this point, it's falling where less probability is. So basically, the error of every single point on my line is following a normal distribution. This distribution is just showing the highest density of the point appearance. So it has nothing to do with the actual horizontal value. You can think about it as a straight line, as a vertical line over here, with this curve showing the density of the point being here or there or whatever. This is the idea to understand the linear regression assumptions. Now, where do we see real life examples height. So let's say the height of kids is around, for example, 1.1 meters, and some kids will be more than this, some kids will be less than this. But if I look at my population, I will see that it's highly concentrated around the specific mean. IQ test, for example, if you notice, the IQ is measuring your percentile based on the people who took the test. So if we look at the population, we can say that there is an average of all the population, or everyone who had taken the test, and you fall under this percentile, or this, or you are one, for example, 1 or 2 or 3 standard deviations away from that middle point. Birth weight, shoe size, for example, we can say that all the adult males, for example, most of them have a mu of shoe size, or a mean of shoe size that is around 42 or 43, and some people go above and some people go below. And it's a continuous distribution, so we can expect to see values anywhere in the spectrum, but with less probabilities. So the exponential distribution, when can we use it? It's frequently used to model waiting times. So if you are trying to model waiting time until the next event occurs, for example, how much time until my phone dies or malfunctions, how much time until this machine I have in my factory fails, how much time do I have until next bus arrives. All of this is an exponential distribution. So if you think about it a little more, it's basically once a specific time starts counting, now it's the highest time. The longer I wait, the time goes below the time that I think the equipment will fail. For example, if I start counting now, it should be higher. If I continue counting until tomorrow, it should be lower because it's minus 1 day. If I count after a month, it should be a little shorter. So my expectation is that the time will come a little sooner, until I get to a point in the future where I expect it to come very soon. For example, if we think about life expectancy. So life expectancy at birth, it's highest. The longer I live, my life expectancy becomes lower and lower and lower. I mean, in the number of years remaining. So the longer I wait, the time expected until the next event occurs becomes shorter and shorter. So how to model an exponential distribution? I only need to know the rate. So if I know the rate of how much time I expect to be waiting at a point of 0, I will be able to model the time at any given point. How is it noted? It's x, random variable, tilde, expo for exponential, and my rate. Its PDF looks like this. So hence, if you notice, if I use the value 0 for my x, it will be lambda times 1, right? So it will be lambda at point 0, and until infinity it will have different values, but this value shrinks very quickly because of the e to the power of minus lambda times x. So as x increase, depending on the value of lambda, it will this will become smaller and smaller and smaller until the value becomes very, very close to 0. Distribution function also can be seen on the very informative Wikipedia page. So as you expect, I will be adding the probability until I reach a point where it's very close to 1. The expected value, if I just take a sample, my expectation that this sample is 1 over lambda. So if I just take a random point in my sample, the highest expectation or the expected value is that it will be 1 over lambda. The variance is 1 over lambda squared. So if you want to know how your actual measurement varies from the expected value, it's around 1 over lambda squared. Where do we see it in real life? As we mentioned, it's all about time or waiting time. So if I want to measure the time between customers, now let's say one customer came, I expect the next customer directly after this customer came to be of a longer time. The more I wait with no customers, I expect that the customer will appear very soon. So it goes less and less and less. So if I say I opened my shop today, I had a customer in the morning, and then I waited 1 hour, no customer appeared, 2 hours. Now the expectation that a customer will appear suddenly, it's higher and higher. The same thing, the time between calls. So if I'm usually receiving calls frequently, I received a call now, right after I hang up from this call, my expectation of a call coming is less. But with time, I expect a call to be coming at any moment. The same thing, they use it to model time between earthquakes. So the point after the earthquake happens is very less likely to have an earthquake as for example 1 year or 10 years, depending on your area from that specific point. Now the gamma distribution. The gamma distribution is used very similarly to the exponential distribution, so it models waiting time, failure times, and so on, but the difference is that it doesn't start at that time. It starts at a low probability, so it can model events that have a peak that doesn't happen at the time 0, but it happens at some time in the future. So the parameters of a gamma distribution are the shape and the rate. It's very important to understand that these common distributions can have different parameterization. So sometimes I can use the shape and the rate, sometimes I use different ways to show this distribution, but the idea of the distribution is the same. But it depends on what parameters I can know about my data that will make me be able to kind of calculate the PDF and the CDF for it. So for this we will use the shape and rate, and I will show you in the Wikipedia page what I mean exactly. It's noted as gamma of alpha and beta. So once I know the shape and once I know the rate of decay, I can tell what is my gamma distribution. So the probability density function looks a little complicated. It's this function. However, if I know alpha, this will be a constant. If I know beta, this will be a constant. And it will only be proportional to x to the alpha minus 1 times the exponential of minus beta to the x. The CDF looks like this, very similar to the exponential. And if you notice the parameterization, it can be parameterized by shape and scale or by shape and rate. And it looks almost very, very similar, because once you know these values, you can plug it and your PDF will end up being the same. So the expected value in our way of parameterizing the distribution, it's alpha over beta. So if I select a random sample of 10 values, for example, I can expect that the mean of these samples will be alpha over beta, and the variance is alpha over beta squared. So once I know my alpha and beta, I can tell a lot by knowing that this population follows a gamma distribution. It models the same things as the exponential distribution. It gives a slight flexibility with where I put my peak. So this tells us that exponential distribution is a special case of gamma. So actually you can get the exponential distribution by setting your alpha to specific values. This will give you your exponential distribution. So very commonly we will see that some distributions are special cases of the others. Now we go into the discrete spectrum. So when we talk about discrete, we talk about values that are not continuous. So I can get 1, 2, 3, I cannot get 1.435, for example. So first we talk about the binomial distribution. When do we use the binomial distribution? The binomial distribution models the count of events that are happening with either two outcomes, two exclusively mutual outcomes. So for example, if my outcome can either be 0 or 1, or success or failure, I cannot have something in between, I can model this data by a binomial distribution. So let's say I'm counting 10 or 5 penalty shots, and I'm just writing down how many goals I score from every 5 shots. So this is a binomial distribution. We call these trials that have only two outcomes, two mutually exclusive outcomes, as Bernoulli trials. So if you think about it, the binomial distribution will have specific values that are kind of clustered around a specific mean. So it kind of brings us back to the normal distribution as an idea of the shape or how it looks like. It's very almost symmetric, always symmetric, especially if the probability of the values of success is around 0.5. So it will be very symmetric, because I expect to, for example, from five penalty shots, I expect that 2 or 3 will be scored. So the highest peak will be in the middle, while scoring all the 5 will be of less probability, and scoring none will be of less probability. And values between are distributed in a specific way. So the parameters, I need to know the number of trials, which is here, for example, the 5 penalty shots, how many trials I'm giving, and I need to know the success probability. So if I tell you that this player has a success probability of 50%, and he's shooting 10 penalty shots, so I gave you N, I gave you P, you can give me the probability. So what is the probability that this person will score less than 6? You can calculate it with the CDF. What is the probability that he will score 5 out of the 10 shots? You can calculate it with the CDF. The notation is B for binomial, N the number of trials, and P the probability of success, or the probability of seeing 1. So what is its probability mass function? It's N choose X, because I'm choosing a specific value of X out of N trials. So I'm saying what is the value at 4. So it's N choose X with X successes. So I'm multiplying P by itself X times. And because we said it's mutually exclusive, so the chance of success, let's say, is 40%, then the chance of failure is 60%. If the chance of success is 70%, the chance of failure is 30%. So I'm just taking the chance of failure, raising it to the power of the number of failures, so multiplying the number of failures by itself, and multiplying the number of successes by themselves. And because there are ways to choose which goals were scored, was it the first shot, was it the 10th shot, was it the 9th shot, I'm using the N choose X. The CDF of the binomial distribution, it will be kind of like an increasing trend. So as you see in the beginning here, it's small, it increases discretely until it hits 1, as we've seen in all CDFs. The expected value is N times P. So if I know that the person's probability of scoring a goal in every shot is 70%, and he's scoring 10 shots, my expected value is 7 goals out of 10, which is the probability of success, 70%, times the number of shots. So the expected value is N times P. The variance is N times P times 1 minus P. So it's N times the success probability times the failure probability. An important note is something that is very related, which is called the negative binomial distribution. I'm not going to go into it in details, but the negative binomial distribution is if I want to count the number of failures, including the last failure, until a success happens. So let's say I want to calculate how many shots do I expect before the first goal is scored, and you can look up the negative binomial distribution in Wikipedia. Where do we see real-life examples of the binomial distribution? The effect of a drug on curing a disease. So the disease can be either cured or not cured. So it's either 0 or a 1. It's either a success or a failure. So if I'm administering a new drug on 1,000 patients, it will have a specific success. And this will be like a representation from my sample of the probability of success in the population. And once I know P, I can make the assumption of how many it will cure in the population. Estimating the number of spam emails. So if I have 1,000 samples of persons' emails, and everyone has a specific number of emails, a specific number of spam, so the email can either be a spam or not spam, I can start formulating an understanding, or I can infer what is the percentage of spam emails. Now to the Poisson distribution. The Poisson distribution is very useful in modeling also count, but in a continuous domain. So if you remember from the binomial, we said that we are counting from a specific discrete domain. So we had 10 shots and we are scoring how many goals. But the Poisson is used to model how many goals in 45 minutes, for example, which is not fixed. It's a discrete value still, that it's not limited by the largest number. So before we couldn't score more than 10, but now nothing stops us from scoring 1000 goals. Of course, theoretically nothing, but practically yes. So the value will go less and less with time. So its PDF or PMF, probability mass function, will look like this. So the probability goes less and less, but it doesn't diminish to 0 because it can be any value. It's a continuous domain. So in 10 minutes, how many bus stops? It depends how many buses pass. It's very probably that, for example, 4 buses will pass, but nothing stops them from being 10 buses if, for example, everything worked out in a certain way. The parameters is very similar to in the continuous domain. We had the exponential distribution, which had the rate. This is very similar to it. So once I know the rate, I can tell what is my Poisson distribution or how it looks like. And it's noted with POI, Poisson, of the rate, lambda. The probability mass function is this formula. So it has the factorial that we didn't see in other formulas, but it's basically the exponential. So this is e to the power of minus lambda. And its CDF will, think about it, it will look like an increasing thing in a faster trend, and then it will slow down a little bit. So it increased fast, and then it started slowing down with higher values. There are useful information also on the Wikipedia page for the Poisson distribution. So the the Poisson distribution is very nice because its expected value and its variance is the same. So if I take a sample of 1000 from a Poisson distributed variable, I expect to see lambda as my expected value, and I expect to see a variance of the same value. So it's frequently used to model real-life events. So the real-life examples is the calls per hour in a call center. Remember, we're not having a discrete spectrum anymore, so the calls can happen in the hour, can be of any value. It's not limited to 10 calls and I'm checking how many of 10 am I actually receiving. No, it can be an infinite number of calls, and I'm just calculating them in a continuous domain. So I'm counting 1, 2, 3, but out of a continuous time or space. So it's calls per hours, number of animals in a specifically defined space or area. So if I'm talking about 1 kilometer squared of a national park, I want to count the number of animals that I see in this area. And I can frequently use my inference from that Poisson distribution to see if the numbers of animals are increasing or decreasing in the wild and so on. The number of cars in a traffic light. So the number of cars can virtually be 0 or 100 or 200 depending on how busy that street is, and I want to make a study to see if this number is increasing. Do I need to increase add a new lane to the street or to the road? So such things can be measured with a Poisson distribution. Now we talked about these 6 distributions that do commonly appear, but there are many more distributions. So some distributions, as we showed, are special cases of the others. In fact, many of them are special cases of the others. I'm not going to go over all of them, but there is a very nice graph that was made by wm.edu. So you can check this website, math.wm.edu. I will add the link also in the description. And it shows you all the univariate distributions. I will explain what is univariate in a second. So for example, you can look at the exponential and you can see how is it related to different distributions. You can look at the gamma distribution and see how the gamma, for example, is related to the normal. This is a very nice page to look and understand distributions a little more if you are interested in them. Now, all what we talked about is the distribution of a single random variable, but there are distributions that are for the multivariate random variable. So let's say my random variable x has x1, x2, x3. Let's say I'm calculating the number of balls that fall in each group. So these will follow a random distribution that is not related to 1 anymore, not 1 variable, but 3 variables. So there are multivariate distributions such as the multinomial distribution and others. And a final note I want to keep you with is that there is a distribution model for almost any real life situation. So your job as a statistician or a data analyst is to look for the model that fits your population well. So once you understand your problem, try to look for common distributions that can be used to model this problem. With this, we completed our discussion on the common probability distributions. Now you can go and learn more about them. You can start thinking about problems that you can model using the distributions we talked about, or even look for more distributions that can fit your problem specifically. If you like the video, please like it, subscribe to see our next videos, and good luck with your data analysis.